Now that we've talked a bit more about triangles and about congruent triangles, we can start talking about the ways that lines, segments, and rays can interact with triangles in particularly interesting ways. One of those ways is through studying what we call perpendicular bisectors. These are not specific to triangles, but when we talk about perpendicular bisectors of the sides of triangles, we do get to some really interesting information. So first, just generally, a perpendicular bisector runs perpendicularly through the midpoint of a segment. So we've seen a bisector of a segment, which means it runs through the midpoint. That's how we get here. Bisector through the midpoint. But when we add the condition that it must be perpendicular and go through the midpoint, that's where we end up with a perpendicular bisector, which is literally exactly what it seems like it should be. A segment bisector that runs perpendicular to the segment itself. Go ahead, pause the video, copy this definition down along with the diagram here that shows the critical information. Come back when you're ready to see an example of what that means in triangles and see the perpendicular bisector theorem. So because triangles and other polygons are made up of segments, we can talk about the perpendicular bisector of each side of a triangle. So it could be that the perpendicular bisector in a triangle goes through the opposite angle to that side. In this case, AC and BD are perpendicular, and the perpendicular bisector happens to go through angle B. But that is a unique case for a triangle. It could also be that the perpendicular bisector of side AC doesn't actually go through angle B because the requirement is that it is perpendicular through the midpoint. Angle B is nowhere near where it would need to be for the red line to go through the midpoint of AC perpendicularly and intersect with it. So we can't necessarily say that a perpendicular bisector goes through an opposite side of a triangle. But in a case like this, we can start talking about some interesting properties, and that brings us to something that we call the perpendicular bisector theorem. The perpendicular bisector theorem says that if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of that segment. In other words, if we know that BD is the perpendicular bisector of AC, then the segment drawn from B to the endpoints of segment AC, that are BA and BC, must be congruent. Go ahead, pause the video, copy this entire slide down, come back when you're ready to move on. So now that we've had some practice with proving triangles congruent and seen some properties of isosceles triangles, you probably are starting to get an idea of how we would go about proving the perpendicular bisector theorem. This isn't a theorem that's specific to triangles, but it uses triangles as a way to show that if BD is perpendicular and a bisector to AC, then the segments drawn from B to A must be the same as the same length and congruent to the segment drawn from B to C. We're not actually going to prove that in this video. That's going to be left up to you at a later point in this module. What we are going to see is now the converse of the perpendicular bisector theorem, which, again, with the converse, just flipping the if and then statements, saying that if a point is perpendicular, or rather, if a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector of that segment. In other words, if we know that AB is congruent to BC, where BD intersects the point AC and the segment AC, and that is true for every point on BD, then BD is perpendicular to AC and AD is congruent to DC. Go ahead, pause the video, copy this whole slide down, come back when you're ready to move on. Again, we're not going to actually see the proof of the perpendicular bisector theorem converse in this video either. That is going to be left up to you at a later point in the module as well. This may be a little bit more difficult to see what the strategy for the proof would be, but it's not actually all that difficult. What we can do by creating segment BD is we can specify something about that segment. We can either specify that that segment is perpendicular to AC, or we can specify that the segment goes through the midpoint of AC. We cannot do both. But one of those is going to be particularly helpful, thinking back to the isosceles triangle theorem. The other, also potentially helpful, not necessarily as helpful as the other one, or rather just has a longer proof with more steps to it. But as you're thinking about this, remember the construction can be used to specify where a segment or a line goes through a single point or 2 points. But if it goes through a single point, we can specify one other property of it. So we're going to choose either for D to be the midpoint or for BD to be perpendicular. And then we're going to prove that the other is true. But again, that's going to be left to you for a point later in the module. If we take the perpendicular bisector theorem and its converse, we end up with something that we could call the complete perpendicular bisector theorem, stated in a different way so that it's not a series of if-then statements. When two converses are both true, and we have a biconditional like this, we often like to create a new phrasing for that statement that allows us to encapsulate both at the same time. And for the perpendicular bisector theorem, the way that we do that is we say that the perpendicular bisector of a segment is the set of all points that are equidistant from the endpoints of the segment. Go ahead, pause the video, copy this definition down, come back to see a little bit more discussion of it, and then to wrap up the video. So this statement encapsulates both the theorem and the converse. If we start with the theorem, where we have a segment that is the perpendicular bisector, then any point on the perpendicular bisector is equidistant from the points of the segment. Well, that's what it says. The perpendicular bisector of a segment is the set. It doesn't say it contains the set. That is exactly what the perpendicular bisector is. So if you're on the perpendicular bisector, you must be in the set of points that are equidistant from the endpoint of the segment. Therefore, we have if perpendicular bisector, then equidistant. Similarly, if we know that a point is equidistant from A and from C, has the same distance there, so that AB is congruent to BC, then it must be on the perpendicular bisector because it's in the set of all points. Therefore, it is on the perpendicular bisector. So we can use the perpendicular bisector theorem anytime we have a perpendicular bisector to show that any point on it is equidistant from A and C, or we can use it to show that a point that has the same distance from two endpoints of a segment must be on the perpendicular bisector, and just call it the perpendicular bisector theorem.